Good afternoon, everyone. My name is Bowen Yang. I am currently a researcher in the Department of Chemistry at Uppsala University in Sweden. So today, I am very excited to share my insights on our recent work regarding the surface treatment of formamidinium lead iodide-based perovskite solar cells, mainly by using an innovative type of sulfonium molecule. So first of all, I would change my I would change it to laser pointer. Okay, so here's the outline of my talk. First of all, I will provide a brief overview of the evolution of perovskite compositions as photoabsorber materials in solar cell application. Then I will explain why we choose formamidinium lead iodide for single junction cells and discuss the associated challenges and our strategies to overcome them. And finally, I would conclude with a summary and outlook in the end. So first of all, why formamidinium lead iodide becomes so attractive now? Here's the evolution of the perovskite compositions used for high efficiency single junction solar cells over perovskite solar cells over the last decade. As we all know that it starts from methylammonium lead iodide and bromide. These materials are very good photoabsorbers with outstanding optoelectronic properties, and the films are very easy to fabricate. However, the drawback of methylammonium-based perovskite materials are their intrinsic instabilities induced by this MA, because it is very easy to volatile, especially under elevated temperature. Although incorporating certain amount of bromide can stabilize the perovskite at some point, it also increases the material's band gap, moving it further from the optimal value of 1.4 EV for single junction solar cells. Therefore, researchers began to play around with the composition of the perovskite material, mainly trying mixing various cations and halides, aiming to make the perovskite more stable and its band gap more ideal for high efficiency and stable solar cells. Then in recent years, we started to realize that formamidinium lead iodide is a very promising candidate with great potential to deliver highly efficient and stable solar cells. This is mainly due to their optimal band gap of around 1.5 EV and also excellent optoelectronic properties as well as excellent thermal stability. So recent studies has already demonstrated that the high performance of these formamidinium lead iodide-based solar cells achieved power conversion efficiency of 25%. However, although FAPI can achieve top efficiencies, they also presents some challenges. So the biggest challenge for formamidinium lead iodide is their phase stability issue in ambient conditions. Its photoactive black phase is not stable at room temperature and undergoes a phase transition to undesired white band gap of yellow phase. Besides, it is also unstable under light soaking and in ambient conditions with water and oxygen involved. Therefore, stabilizing black phase formamidinium lead iodide, perovskite, and solar cells while maintaining its high efficiency is an important task to address. So how do we achieve this? Because in a single junction perovskite solar cells, both efficiency loss and degradations in general are initiated at grain boundaries and surface or interfaces of the perovskite layer, where these defects and also mobile ions tends to accumulate under external stress, therefore suppressing the perovskite bulk as well as its adjacent interface defects, along with inhibiting different kinds of mobile ion migration is very critical to achieve perovskite solar cells' long-term stability. So in this regard, we realized that there are mainly two strategies developed so far that can efficiently stabilize perovskite film in general. One is to stabilize the perovskite bulk through additive engineering, and the other one is to stabilize the surface through surface engineering. So same strategies apply for stabilizing FAP-based perovskite solar cells. To modify the bulk of FAP perovskite, additive engineerings with, for example, methyl ammonium chloride has shown great success already from literatures. So researchers have found that while adding certain amount of methyl ammonium chloride into the formamidinium lead iodide perovskite precursor solution, this can significantly enhance the quality of the resulting FAP film. And the additional methyl ammonium chloride can dramatically increase the perovskite grain size, improve the morphology and crystallinity, and also it can reduce the bulk defects. As a result, the perovskite film quality and stability are greatly improved. Aside from bulk engineering, my work is mainly focusing on surface engineering of perovskite film. So here I summarize some key factors that typically we consider when we're designing and employing materials for surface engineering on perovskite films in general, particularly in the architecture of NIP cells. Hopefully, this will provide you an overall idea of our main approach. So basically, we start from material design and development, wherein we consider not only the structure and properties of the designed material itself, but also examine its interaction with the perovskite layer. Additionally, we evaluate solvent effect, for example, which solvent would be the most suitable, considering factors such as polarity, solubility, and their effects on perovskite during surface treatment. On the other hand, we also dive into its deposition engineering, which includes exploring the deposition method and determining whether post-annealing is needed regarding to each specific material applied. So overall, the evaluation and optimization process starts from material design and engineering, and then all the way to the device engineering. So our story starts from designing a material that can form a 2D layer on top of the 3D perovskite through surface treatment. Similarly, with the idea of the commonly used PEAI, for example, and other ammonium salts for post-treatment. The reason why we want to modify this, the structure of this PEAI is mainly because we observe that the PEAI-treated perovskite films are prone to aggregate due to this pi-pi interactions induced by these benzene rings. Therefore, we design a new material, CMAI, where we replaces the benzene rings with cyclohexene. So this replacement can weaken the intermolecular interactions within the passivation layer. Therefore, it can prevent the CEAI from undesirable aggregation as this PEAI does. So with this, the film becomes more uniform with fewer defects. In this way, both the performance and stability of the CEAI-treated solar cells get dramatically improved. In addition to investigating the surface materials, we then examine the effects of the solvents during post-treatment. For example, in our previous study, we developed another material, CMAI, with a shorter alkyl chain length compared to the CMAI, so that it can dissolve in different kinds of low polar solvents. By combining surface treatment with CMAI in different solvents, we noticed that the choice of solvent for post-treatment could affect or influence the film morphology, the formation components on the surface, and also the surface strain of the perovskite film. So these factors could eventually affect the quality and the stability of the perovskite film and the resulting solar cell devices, which needs to be considered. So for example, in this study, we compare surface treatment of CMAI molecule in both IPA and chloroform. First of all, when we dissolve it in IPA, we found very nice, compact, and uniform perovskite surface, as you can see from this SEM and AFM images. However, exposing the perovskite surface to IPA simply could, on the other hand, pose a risk of creating a lead iodide-rich surface. As you can see, these little white bright features, they're lead iodide. So this can generate defects and facilitate perovskite degradation. Therefore, we replace IPA with a low polarity solvent chloroform. And we found that with only chloroform post-treatment on top of perovskite, it showed minimum solvent effect on the surface during the post-treatment. So then we dissolved the CMAI in chloroform and then applied it on top of the perovskite film. It is very interesting that we found this morphology of the film performs differently with the one treated with CMAI in IPA. From this SEM, you can see this contour line texture appears in the CMAI in chloroform sample. And the SEM also show a reduced surface roughness. So that means if you use different solvents to carry the same material for post-treatment, then probably you can come up with a different surface morphology. And then further investigation were conducted to understand the underlying reasons. So in particular, XRD measurements of the FAPI film post-treated with CMAI in different solvents show that both in IPA and in chloroform-treated films, they exhibit low diffraction signals, new diffraction signals at low angles. But if you look closer into it, they seem not at the same position. Therefore, after zooming in, we found that based on this XRD fingerprint of the CMAI molecule and the formed 2D species, when using the IPA, the majority of CMAI molecule integrated into the 2D perovskite phase, while only a small amount remained unreacted on the perovskite surface. In contrast, after treatment with CMAI in chloroform, the formation of CMAI predominated with only a small amount of two-dimensional species on top. So we attribute this phenomena to the different solubility of the main component, FAI, in the 3D FAPI perovskite. Because the FAI dissolves well in IPA. This is because it has a high polarity and it also forms hydrogen bonding in IPA. But it shows very limited solubility if we dissolve it in chloroform. So in this way, the FA in the 3D perovskite partially dissolves from the perovskite surface when exposing to IPA solvent, and it removes during the spin coating process. Therefore, the resulting vacancies enable a reaction between the remaining lead iodide from the pristine perovskite and the newly introduced CMAI. Therefore, it forms a more pronounced 2D perovskite layer on top. That's why we see different species formed when perovskite treated with the same surface material but carried out in different solvents. In addition, we also discovered that the distinguished surface reconstruction process by post-treating FAPI with CMAI in different solvents could also influence the residual strain of the perovskite surface, which has been recognized as one of the critical source for perovskite solar cell instability. Combining all the effects, we observed a dramatic improvement in both device performance and stability of the treated cells. However, despite the significant stability enhancement compared to the reference cell, the CMAI-treated devices still show noticeable degradation under only 1,000 hours MPP tracking. So this operational stability of the surface passivated FAPI cell is of course improved if you compare with the reference cell, but it's absolutely not enough, especially for the need of commercialization if you compare it with the well-established silicon cell. And this is the same problem. It happens to all the state-of-the-art high-efficient perovskite solar cells in general. It's a big challenge, at least at the current stage, to achieve high-efficiency perovskite solar cells and meanwhile maintain its good durability. For example, here I listed the operational stability of state-of-the-art high-efficient solar cells with PCE of over 22% from literature. So by looking at this, we can clearly see that The perovskite solar cells based on mixed cation and mixed halide marked in those blue ones are relatively stable. But still, the majority of these efficient cells show obvious degradation within 2,000 hours aging under MPP tracking. And in comparison, although pure FAPI-based solar cells, like these ones marked in green, they exhibit higher device performance in general. Their operational stability is rather poor. The best ones degrade more than 5% of its initial performance within only 1,000 hours MPP tracking. So in this case, we're considering whether there are better materials that can stabilize FAPI-based solar cells more efficiently. And an exciting news is that we recently discovered a new type of surface material, which is sulfonium molecules, that show great potential to stabilize formamidinium lead iodide perovskite film and the solar cell. So in this work, we innovated this new type of sulfonium molecule, we call it DMPSI, by using it to post-treat on the perovskite FAPI surface. We delivered the PCE of over 23%. And most importantly, at the same time, the DMPSI treated FAPI cell shows outstanding operational stability with less than 1% PCE drop for over 4,500 hours aging at MPP tracking. So the innovation of utilizing sulfonium-based molecules to stabilize the perovskite surface are driven by the unique geometry with this largely strengthened chemical and humidity stability provided by these sulfonium-based cations. For example, a new one-dimensional perovskite based on this trimethyl sulfonium cation has been synthesized earlier, which exhibits elevated chemical stability. And similarly, a fully alkylated sulfonium salt, BDMS, was introduced into methylammonium lead iodide bulk, perovskite bulk earlier, and exhibit a significant enhancement in device performance under especially humid conditions. Although this device performance are not pronounced in this case, they're compatible with their reference cells. We got inspired that such sulfonium molecules might have great potential in stabilizing perovskite in general, and meanwhile also can hopefully improve the device performance, especially if they can be used on top of the perovskite surface. However, the main limitation at the moment to use this aliphatic sulfonium molecules for surface treatment is their poor solubility in low polar solvents, including IPA and chloroform, which are the most commonly used surface treatment solution solvents. Therefore, when we designed the material at the very beginning, our first aim was to enhance the solubility of the sulfonium salt in low polarity solvents for its successful use on top of perovskite. And in the end, by tuning the structure mainly through the introduction of a benzene ring, we synthesized this molecule, DMPSI, which show much improved solubility in solvents like chloroform, although it remains insoluble in IPA. But as our previous work shown that chloroform has advantage even than compared to IPA for post-treating FAPI films. So the solubility of this material in chloroform makes it already possible for surface treatment, and we were very happy with that. And then after the synthesis, we evaluated the stability of this material by storing it in ambient air with certain humidity and tracking its components by NMR. So as you see from the spectrum, there's no water peak detected after 6 months storage in ambient. This indicates that this material is very stable in ambient. So with such low water uptake property of the sulfonium salt, we expected that it can effectively improve the hydrophobicity of the FAPI film upon surface treatment. With this, we deposited a layer of 1 to 10 milligrams per milliliter of the sulfonium molecule on top of a FAPI film. As you can see from the contact angle, a pronounced increase in contact angle is clearly observed from around 55 degree of the reference FAPI to around 90 degree of the perovskite films treated with different concentration of DMPSI. So this suggests that the post-treatment of the sulfonium salt can provide a more hydrophobic surface. And then we expose these perovskite films to ambient condition. So from these pictures, we see that the reference FAPI film already becomes brownish after exposure to ambient for like 10 days. However, the treated FAPI films remain blackface even under the same condition for 2 years. So we keep track it every several months, and the pictures are shown here. And later on, I was very surprised to see that those films we kept tracking still look quite black after being exposed to ambient condition for 3 years in our laboratory. The paper has been published, so I just accidentally saw these films, and I was very impressed with this performance. Anyway, we further exposed those perovskite films to a high relative humidity of 85 to 95%. There are the photos of the films and their different concentrations of this passivation material. And then the corresponding XRD measurements at a certain time period. So we can see clearly that after exposure for 24 hours, the reference FAPI film experiences a rapid phase transformation from black phase to yellow phase. And you can see the color is also very, very yellowish. However, in sharp contrast, the films treated with moderate quantity, let's say from 1 milligrams to 5 milligrams per milliliter of this DMPSI remains mainly black. However, we also observe that the perovskite film treated with a largest amount of, let's say 10 milligrams per milliliter of this sulfonium salt degraded severely. Especially it creates this inhomogeneous surface, unlike the pristine FAPI film. This phenomena is very interesting to us because we expected to see that the more material it covers on the perovskite surface, the more stable the film might be. However, we understand this behavior by cross-checking these as-prepared film morphologies measured by SEM. So from these images, we can observe that a dense and pinhole-free polycrystalline perovskite film with micrometer-sized grains becomes more uniform after surface treat with 1 milligrams per milliliter of this DMPSI. And as the concentration of this material increases to 3 and 5 milligrams per milliliter, a uniform and smooth surface is still observed. However, the new species seems to occur. We'll figure this out a bit later. But when the perovskite surface treated with a large amount of DMPSI on the surface, we observe a lot of cracks, where you can see in these red circle areas, for example. So we attribute this poor surface coverage to the aggregation of the excessive DMPSI on the surface. So these cracks could easily induce degradation pathways for moisture, for example, from external atmosphere to penetrate into the perovskite bulk, especially under high humidity, relative humidity conditions. So this would lead to an accelerated degradation process. That is why we see severe spot-like degradation centers in these films and their very high relative humidities. Then besides the stability of the perovskite films and the moisture conditions, we also probe their light soaking stability by performing wide field hyperspectral mapping of both reference FAPI and the DMPSI treated film. So from these videos, it is very clear that during the mapping, which is carried out under light soaking for 10 minutes with one sun intensity, illumination intensity under ambient condition, we see that the intensity of the reference film drops dramatically, meaning that the initial FAPI phase is highly unstable in this condition. However, the DMPSI treated film remains very stable. It shows negligible changes in PL intensity. So this indicates that our surface treatment has turned an intrinsically very unstable material into a much more stable one, especially under light soaking in ambient condition. So far, the above mentioned evidence clearly show that our surface treatment with this sulfonium molecule can significantly improve both moisture and light soaking stability of the formamidinium lead iodide film. And next, we wanted to understand why this is the case. What is the stabilization mechanism? Specifically, we make this, what makes this sulfonium molecule different compared to our commonly used ammonium salts, for example, for surface treatment? One of the most important and interesting discoveries in the study is that we found a formation of an interesting new species on the perovskite top surface after this treatment. So as mentioned earlier in the SEM images, we suspected that. And now this suspicion is further supported at the atomic level by examining the scanning electron diffraction pattern. So comparing with this reference formamidinium lead iodide sample, we clearly observe a new crystalline species extracted from this region of the DMPSI treated perovskite sample. But what is this composition of this newly formed species? Would it be solely sulfonium salt itself, or newly formed like low dimensional perovskite species as normally occurred in ammonium treated perovskite films, or would it be something else? So by comparing the XRD patterns of those DMPSI treated FAPI films with the DMPSI salt itself, we can exclude the possibility that the new species solely consists of sulfonium salt. This is because this DMPSI salt is amorphous and it does not exist distinct XRD patterns, whereas the post-treated films show some small peaks at low angles. And also with it solid-state NMR, it shows interactions between the DMPSI and FAPI film. For example, we see obvious peak shifts of DMPSI after treatment on the FAPI films, both in this hydrogen NMR spectrum and carbon NMR spectrum. So this indicates a change in chemical environment of DMPSI upon treatment. In another word, these peak shifts suggest the interaction between DMPSI and the FAPI. Then would the new species be like various kinds of low-dimensional perovskite species? Well, unfortunately, the XRD result did not support this hypothesis. So the XRD peaks from the DMPSI treated FAPI films cannot really align with any of these low-dimensional species we can thought of. And eventually, after many tests, we found that when we mix the DMPSI with FAPI in certain ratio, it shows similar XRD patterns with the treated perovskite films. So we define this new species as a mixture of DMPSI and formamidinium lead iodide. This is very different compared to the formation species of previously reported materials upon surface treatment on perovskite. So this statement can also be proved by the SEM images because both films show very similar morphology. So on the left side is the SEM image of the FAPI film treated with 10 milligrams per milliliter of this DMPSI salt. Well, on the right side is the SEM image of the solution that we mix the DMPSI with the FA-lead iodide as a ratio of 1:5. And you see the films looks very similar, especially also including these cracks. Then with this mixture species on top of FAPI film, we found it can not only stabilize the film, as we mentioned, but it can also improve the film quality, similarly to other passivation materials. And then this leads to a significant prolonged of charge carrier lifetime, which enables high quality perovskite film with notable reduced non-radiative recombinations. And then consequently, the device performance is enhanced, increasing from over 21% of the reference cell to over 23% in the best performing cell with 3 milligrams per milliliter of this DMPSI salt. More interestingly, in this work, we spent quite a lot of effort on testing and understanding the device stability as well upon treatment under various aging conditions. For example, we storaged the unencapsulated cells in our drawer in ambient condition for over 2 months. And from these pictures, those ones within this red box is DMPSI treated, and the black ones are control devices. And these two are fresh samples like as prepared, and these two are the aged cells after in ambient for 2 months. So visually, we can see that the aged control device has turned light brown. And also we can clearly see the, this one. Also, we can clearly see the gold electrode from the backside of the glass right here. So this indicates a severe degradation of the control cell after aging. However, the device with the DMPSI treated remain completely black. This is also confirmed by measuring the XRD of the aged devices, where the control cell exhibit this obvious delta phase, but the DMPSI treated one remain completely black phase. And then this XRD we plotted in log scale, so any little species can be observed very obviously. And then in addition to testing ambient stability of these devices, we also evaluated the encapsulated devices under damp heat and also a thermal cycling. We found that the reference cell also show pronounced degradation in both cases, whereas the surface treated devices remain quite stable in both scenarios. So what I wanted to highlight in the end is that our surface treatment with this DMPSI material has achieved remarkable operational stability. So we exposed those unencapsulated devices to MPP tracking under continuous one-sign illumination in inert atmosphere with nitrogen flow at room temperature for about half a year, over 4,500 hours. And this is the result. So we see that there is an initial rapid degradation, a burn-in region within especially the first 30 hours in the control cell. This leads to a rapid PCE drop. So this phenomena is similar to other reports on from a lead iodide-based solar cells, and is typically attributed to the redistribution of charge defects. And then this is irreversible. This is reversible, sorry. And then subsequently, there is a slower decay that presents. This is due to the irreversible chemical reactions through migration, which gradually cause this irreversible degradation of the device. And then in overall, it leads to about 20% efficiency, percentage loss of its initial performance for this control FAPI cells after aging under MPP tracking for like 1,500 hours. So this degradation mainly comes from the fill factor and VOC if you zoom into these parameters. And then in contrast, the DMPSI treated devices show excellent stability under the same operational condition, with negligible PCE drop after long time. And making a linear exploitation of this data yields a theoretical T80 value of over 9 years. So this makes our treated devices among the most stable ones reported so far, and meanwhile with high efficiency at the same time. We attributed this excellent stability of the DMPSI treated devices to the multifunction of the sulfonium molecule. So as we proved earlier, post-treatment with the sulfonium salt can enhance moisture resistance at the perovskite surface, and then it can form a compact capping layer through this intermolecular interaction between formamidinium lead iodide and DMPSI. And it can also passivate the perovskite defects. So this results a better quality and stability of the perovskite film. And then additionally, by analyzing the solar cells before and after aging, before and after operational aging test, we found that this surface treatment can also efficiently inhibit the ion migrations, especially the gold and iodide ions within the device upon aging. So in this case, the degradation process induced by defects has been inhibited due to the passivation effect of the surface treatment. And then the ion migration-induced degradation process has also been prevented. So this combined effect enabled the excellent stability of the passivated device. And then to further prove the inhibition of ion migration effect, we did some top seam measurements, elemental depth profile measurements for both reference FAPI devices and the passivated devices before and after MPP tracking for over 4,000 hours. So this one is the full spectrum of top seams, and the solid lines indicates the fresh devices, the dashed ones are the aged ones. More specifically, we can look particular into iodide ions and gold ions diffusion. So we can see that both the as prepared, the solid lines control and treated devices have similar signals occurs for iodide, for gold and for iodide. However, as expected, for the control cell after aging, the signals of iodide increases in the whole transporting layer, and the signals of gold occurs in the perovskite layer. So this provides direct evidence for ion migration within the layers of the reference device. So such severe ion diffusion creates not only trap defects, but it can also create a lot of shunts across the cell. This would eventually lead to a dramatic performance drop, especially in VOC and fill factor. However, we don't see much iodide and gold diffusion signals of these diffusion species for the DMPSI treated devices. So this evidence clearly indicates that the introduction of these sulfonium molecules at perovskite surface can effectively suppress the iodide ion and gold ion migrations, and therefore provide a good stability. So with this, I would like to summarize my talk. So as mentioned, formamidinium lead iodide stands as a highly desirable photoabsorber material for achieving highly efficient and stable perovskite solar cells. And then we noticed that additive and engineering are effective strategies to improve performance and long-term stability of the devices. And then as I summarize that there are some key factors needs to be considered while implying or thinking of modifying a surface of the perovskite layer, which includes material effects, solvent effects, and also device engineering as well. And then in our work with the sulfonium molecule treated perovskite solar cell work, we noticed that one surface treatment step with the sulfonium molecule can lead to a very outstanding stable FAPI film and devices. So this gives us provides a very strong indication that perovskite thin film technology has the enormous potential to hopefully fulfill industrial protocols and can compete with silicon-based solar cells for large-scale and industrial productions. However, further investigations ahead to unveil more possibilities and potentials of the sulfonium molecules for various use in perovskite solar cells. And there are still a lot of things that are still unexplored. And last but not the least, I would like to thank our main collaborators for their excellent contributions and our fundings. But also thanks a lot for your attention. I'm glad to take any questions from the audience. And please feel free to reach out in case you have further questions even afterwards. Thank you very much.